Well, good afternoon. At least it's afternoon here now. Here and now it's afternoon. In Wisconsin, it's still morning. I don't know when you're watching this. It doesn't really matter, but it's always kind of a fun way to introduce the video. Today we, okay, so let me kind of back up a little bit. For the most part, what we've done so far is free body diagrams, stresses, review, static failure theories, new-ish. But now we're going to start the real new stuff in what I personally think is the most important topic of the semester, and that is that of fatigue. Everybody here has probably everybody here has taken a paper clip and you bend the paper clip a bunch of times and then the paper clip breaks, right? There's no way you're strong enough to just exceed the tensile strength of steel with your fingertips. But if you do it a bunch of times, it breaks, right? So what actually happened there? That's a fatigue failure. We probably all knew that. But we're going to investigate how this happens and what it's about. All right, so let's, without further ado, let's take a look. So this is a bit of a long lecture, so I kind of split it into two. So hopefully that makes it a little less painful to watch. So this is part A of the fatigue, right? What is fatigue? So it's some sort of loading, right? Your fingers on the paperclip, for instance, that produces stress, stresses that are variable, repeated, alternating, or fluctuating. Okay, that kind of captures it all. The maximum stresses could and likely are well below the yield strength, right? So not even much less the ultimate strength than below the yield strength. And then the failure occurs after many stress cycles. And the failure is by sudden ultimate fracture. We'll talk about that just a little bit. And frequently and insidiously, there's no visible warning in advance of this failure. All right. So, oh, whoa, holy cow, font problem, underlined, bold. In cyclic loadings, stress concentrations matter, even in ductile materials. Yeah, so for the most part, we ignore stress concentrations in a ductile material because there's load sharing, right? One fiber stretches, the fibers next to it pick up the slack, and no big deal, right? But in cyclic loading, stress concentrations are a big deal. We'll see some examples of that in just a bit. All right, so stage one, right? These are the stages of fatigue loading. I'll do these in red. Stage one is right here, right there. So a tiny crack forms. Tiny crack. We might even call that a micro crack. Right, and it's on the order of crystals, right? It's not a crack that you can see. It's a crack that's the size of the metallic crystals. Very, very small, that forms, right? Now that becomes a stress concentration, right? And every time we repeat the loading, the crack forms here, and then the crack gets a little bit bigger, and then the crack gets a little bit bigger. And then now, so, this is a bolt or something like that. It originally had some cross-sectional area, and now it's got less because this crack is formed all the way across. So this is at the surface, actually. At surface, right? And this crack, we cycle the load again, it gets bigger, cycle the load again, it gets bigger, cycle the load again, it gets bigger. Now I'm drawing these huge. There's halfway across in 5 cycles, but in reality, the difference between this is on the order of micrometers or even nanometers, right? Really, really small progressions. So it takes thousands and thousands of cycles to do this, hundreds of thousands of cycles to make it all the way across. And because it looks a little bit like the waves on the beach, right? These things here are called beach marks. Right, those are the beach marks there. Now, eventually, right, this bolt was strong enough when we first selected it, but now, by the time we get to here, this is all the area we have left. So this is a much reduced area. Much reduced area here, right? And that's not enough anymore, right? It's not enough to carry whatever load we're applying to this. And so ultimately it fails by a simple ultimate failure, right? We just exceed the ultimate stress at that location and it fails. So this is, I think, is a very, very compelling slide. I'm not going to quiz you on it, but I think it's important to know as an engineer. Here's an example where just some tiny little crack started at the surface there and it worked its way across until there was a failure. right? Here is a mild stress concentration, so there's a little wiggle. There's a little wiggle in that area there. If there's a severe stress concentration, you might get beach marks that start at several different locations. And then, the same thing happens. So the high nominal stress, right? So large area fractures. That's important to note too. Whereas with a low nominal stress, right, we have to get, this area survives. This area is sufficient, right? So it really, a small fraction of the area was still enough to hold until the very end under that low nominal stress. And what's cool about this is that they're experts, right? And their entire career is based on looking at these failed parts and identifying what happened, right? What was the original geometry like? How long did this take? What were the cycles like? So that, and I hate to be such a kind of a Debbie Downer, but if you wind up in court someday and you say, no, there weren't any stress concentrations in this particular component, and the expert witness says, here's the cross section of this stuff, yes, there was a stress concentration right here. It's amazing the detective work these expert witnesses can do. So that's kind of interesting, right? Ideally, you don't wind up in court. Chances are you will, so just be ready for it. All right, don't lie. Just be honest. Document what you do. All right, so that's that. Some examples, right? So here was some sort of a shaft, right? And maybe there was a grease hole here. There's a grease hole that went in and out of the shaft, and then so this grease hole goes in and out, or coaxial hole. And this is a radial hole. That one is radial, and it didn't line up quite right, so we had a sharp corner here and a sharp corner there, and that was a high enough stress concentration that's where the micro crack started. The beach marks propagated across until we had the ultimate failure there. All right. Here's another one. This is particularly scary because the imperfection was in here, right? This is the initiation was interior. Initiation was inside there. So there's no way to see that. It's impossible because this is loaded axially. We'll talk about this more in a little bit too. The maximum stress, the stress is evenly distributed, right? So stress in axial loading is evenly distributed. So that crack could start anywhere, not necessarily right on the surface. There's a forging flake. A lot of you aren't really thrilled about ME313 and 314. How this stuff is manufactured matters. It really matters. So in the forging process, there's a little flake in there, and that's where the crack started. All right. Here's another one. I could go on and on about these things. Even something clever like stamping. A lot of times you stamp like what batch number it was or the date it was manufactured or a logo or something like that. Even that little stamping could be enough of a stress concentration that under repeated loading, the crack could propagate and it could result in failure. That looks like a rail car wheel or a double flange trailer wheel, maybe a rail car. So this is one, right? I like the ocean. Right? Pretty much got the ocean in the background of all these videos. This is an oil platform, and off the coast of Norway, if I remember correctly. And it sits on these four big legs, but it just sits there, right? It sits there, and a bunch of people, typically a bunch of dudes, live on this oil platform and they work on the oil platform. So why would that be a fatigue failure? Anybody know? Pause, think about it. Waves, right? Just the little tiny wave action, right? Maybe in a big storm, some bigger wave action causes fatigue failure. Fortunately, it happened a little slowly, and in this particular incident, as I recall, some minor injuries, but nobody died. All right, so not a catastrophic loss of life here. Now, as you might guess, this one was a very catastrophic loss of life. I believe this was in Germany. If you've ever been to Europe and traveled around Europe, either ride the cheap trains or the nice ones. These are the Intercity Express ICE trains. So if you can buy the expensive ticket, you can cruise around Europe like that. I never did. So Yeah, so this is a fatigue failure where many people died. I think 150 some people died in this particular rail car accident, and the investigation discovered that it was a fatigue failure on one of the axles that caused this. More people die. In fact, I'm going to show my face for this. More people die due to fatigue failures than any other kind of engineering or component failure, right? So fatigue is literally deadly. So that's why I think it's such an important thing to talk about. All right, so fatigue life methods, right? So how are we going to study this? There is the stress life method, where we say, okay, this is the stress, and it's an alternating stress, goes back and forth. How many cycles of this particular stress can we handle, right? This is the least accurate, right? Particularly for the low. So if you get under 1,000 cycles, stress life is not very accurate. But it's the most traditional, and it's the easiest to implement. Hence, that's the one we're going to do. Slightly more accurate would be the strain life method, but that really gets into the math is more complicated, the form is more complicated, it's much more material dependent, and it's just harder, right? We don't have time to do all these three things, so we're just going to do the first one. And then finally, there's linear elastic fracture mechanics. I'm not a fracture mechanics guy, I'm a fluid mechanics guy, but it's all continuum mechanics. But I don't know anything about this. It's much more complicated. It's the most accurate, but again, we don't have time to do it. All right, so what is the stress life method? What we do is we take a very special specimen here, right? And so you can see the dimensions. So this is the test sample of the material, right? We're trying to identify some material properties here. And we put it under 4-point bending, right? How do we do that? I think we support it. We pull down here, and we pull down here, and we push up there, and we push up there. The result of that is there's no transverse shear. It's just in pure bending, 4-point bending. And then we spin this, right? And then so, on the top surface here, that's always in tension. So as we rotate through that, it goes from tension to compression to tension to compression to tension compression. So it's a fully reversed repeated loading. And eventually it fails. And we just count how many cycles until it fails. Now, for reasons we'll talk about shortly, it's very carefully machined, right? So those radii are very tightly controlled. The surface finish is very tightly controlled because we want to get a pure material property out of this. We want material property. We don't want geometric factors. So by the careful machining, careful polishing, we can eliminate that. It'll make more sense in a second. All right, and then so we get these data, we put several different loads on it, and we can discover that at relatively high loads, obviously if we stress it to its ultimate tensile strength, right, it breaks after how many loads? 1. Okay, that makes sense. That's why it's called the ultimate tensile strength. And then we can go up to about 1,000. So this is about 1,000 cycles there. And these are all, the yield strength is probably somewhere around here, right? So we're above the yield strength, so we're yielding this thing back and forth, back and forth, back and forth, and it fails somewhere under 1,000 cycles, right? Now, something really cool happens, and this is for steel, right? For steel, very important. At 10 to the 6th cycles, so right here, right, 10 to the 6th, it kind of flattens out. What does that mean? So at roughly 90%, so this is approximately 0.9 times SUT, roughly 90%, right? We get this linear region from 1,000 cycles at 90% down to 1,000,000 cycles at a half. So this is about 0.5 SUT, all right? Round numbers. 90% to 50% of the ultimate tensile strength, and we get a linear relationship, well, a log linear because this is on a log scale, between the number of cycles that this thing survives, right, the number of cycles, and the stress that it can withstand, right? Now, when we put these specimens, this is spinning at 1,800 RPM or something like that. It spins and spins and spins. So to get 1,000,000 cycles, right, that's half a day, right? To get 10 million cycles, no, 10 million, 100 million cycles, that's 100 million cycles, right? That takes 40 days to run that test, right? So when we did the fatigue experiment in 307, it's too much work for one credit. We you can see why we had very high stresses in order to get this thing to fail quickly, right? There's no way we could do a 40-day experiment in 307. But steel has this interesting property that as long as we're below this critical stress here, so say I'm here, I'll do that in blue, random color. So if I'm at, say, 20 KSI, right, I can run this thing forever, and it's never going to fail, right? So this is called the endurance limit, right? Okay. What else do we have here? So the stress levels below, so if I stress it below the endurance limit, right? Remember this is SE, endurance limit there. This thing will last forever. I can stress it, release it, stress it, release it, stress it, release it, or reverse it, infinite number of times, and it'll never fail, right? Between 10 to the third and 10 to the sixth. So let's do that in green. So in this region here, right, we can predict this log linear. So I can say, well, I'm going to stress it roughly 80% of its ultimate tensile strength. Then you can guess or predict how long it's going to last, right? So for instance, I'm designing race car engines, the time trials, and they actually do this. So in race car time trials, and you can, it varies from class to class. Let's. Am I here? Hello. There we go. So these race cars, the way the time trials work is they get one lap to get up to speed. They run one lap as fast as they can, and then they have to make it around a pit row, right? They have to get back to the home base. And so they actually design these components, right, to be as light as possible. They shave every gram they can, such that they said, well, we're going to run at 8,000 RPMs, and it's going to last us about 2.5 minutes. So we calculate how many cycles are we going to need, and let's design the part so it just barely withstands that number of cycles, right? Of course, for the full Indy 500, right, that's well over 1 million cycles, so everything has to be below the endurance limit, right? So it's knowledge of the finite life is important in many applications. In this class, however, we're going to pretty much stick to infinite life. All right, what's next? So here's where the data comes from. As I mentioned, a very, very special specimen. What I think is great is, so they've got a really nice model of the motor and the revolution counter and all these nice bearings and stuff like that. And then here they have this really, change that. Let's get rid of that. Change it. So here they have this nice wire, right? Couldn't you come up with a better drawing of a wire, right, for all the good graphics you have? But whatever. And so this is called SN prime, right? They use this machine to count the number of cycles it'll last at this certain stress level, and they call that SN prime, the ideal endurance limit, right? But this is so carefully contrived and so carefully controlled. In the real world, a real oil rig, a real train car, a real sailboat mast, it's not that contrived. There are other factors we have to consider. So it's going to weaken our material or increase the net effect of our stress. All right, so it's important to remember this is all laboratory based. Lab-based data. Now, I love being in the lab, and I love getting data in the lab, right? But I also like stuff to work in the real world. So how do we do that? One more thing before we get into that. So as we mentioned, there's this linear in the green section here, a log linear relationship between the stress and the life, hence the stress life method. Let's slide that up a little bit. So there's the number of stress cycles and then the fatigue strength at that stress, or at that number of cycles. So that's log linear. This is really just y equals mx plus b. Let's write that in blue still. So this is just y equals mx plus b, redo in log, redo coordinates. And I'm not going to go through the derivation, it just takes a little while, but it's pretty slick, right? It is really just a straight line, y equals mx plus b. based on some stuff that we know. For instance, how strong is it for 1,000 cycles? What's the endurance limit? And that's all we really need to know, right? It's just those two things. And then we can get the predict the life based on the stress, okay? And I'll put that up in the on the Canvas page. All right, so as I said, this is all based in the lab, right? We do this carefully controlled experiment to figure out what is the material property? What is the endurance strength as a material property? But I'm not testing material specimens in the real world. I don't build my sailboat or my rail car or my oil rig out of lab specimens. I build it out of real stuff, right? The surface finish might not be great. It might be really much bigger than the sample. It might be exposed to salt water. It might be exposed to axial loading instead of bending stress, blah, 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 blah. So I have to take this lab-based material property, adjust it, and then come up with some endurance strength or fatigue strength that I can actually use in my design of this part. All right, so back to this. And so what, hello, there we go. So what we do is take our SN prime, right? Remember, this is the lab test material property. Right? And then this is what brings us to the real world. Right? These numbers are based on a lot of experiments, right? And they're all less than one. So, say I've got something that's good for 300 megapascals, right? For the SN prime, the material property is 300 megapascals. I multiply it by, say, 0.8, and then 0.7, and 0.89, and 0.4, and 0.119, or something like that. And I can go from my endurance strength of 300 megapascals, and it drops very, very quickly. Okay, it winds up being on the order of 100 megapascals or less once I incorporate all these real-world factors, right? How do I load it? How big is it? What's the surface factor, surface finish like? And then there's, of course, reliability factor, which seems like voodoo, but it's not, right? We'll take a look at that. The load factor, right? Different loadings have different stress distributions. Okay, why is this? We know that the original test was done in pure bending, right? Where the maximum stress is at the surface, right? So only along the surface is where the maximum stress is. So we kind of need to find an imperfection that's somewhere near the surface, right? And that's where this initial crack, the fatigue failure, is going to start. However, if we load it, for instance, axially, then it's not going to last nearly as long. Why? Because anywhere on the whole cross-section of the specimen could there be an imperfection for this to start, right? This is why axial loading and fatigue is a little bit dangerous. And so we've got some other tables. This isn't really the best plot to show this, so we'll talk about it later. Gradient or size factor, this is also related to that, right? So here are 3 pictures, right, where they all have equivalent maximum stress, right? So equivalent sigma max for all 3 of these. Now, of course, this one has much greater load, much higher load, right? And this is a much lower load for that one. But the key thing is they all have the same stress at the surface, okay? Well, what has to happen for fatigue failure to start? We have to find some high stress that coincides or is coincident with some imperfection in the material, right? Well, which one of these has more imperfections that are exposed to high stress? Look at all this area here. This whole area is exposed to a really high stress, right? Now, steel is not a homogeneous material. It's not a continuum. Steel is made up of little crystals. The crystals in this one are the exact same size as the crystals in this one, right? So the number of crystal boundaries, the number of crystals, the number of imperfections, right, per unit volume is the same. So the chances of me having a high stress at an imperfection is much greater with the bigger one than it is for this one, right? So it's counterintuitive, but the bigger one is likely to fail first, right? Because there's a higher probability that my high stress region comes across an imperfection just because there's more crystals in the big one and there's more chances for an imperfection to exist, right? Very counterintuitive. Bigger ones do worse in fatigue. And then this is really, I should make this the first one, but for whatever reason I didn't, is the surface finish, right? Typically, bending stresses cause things to fail, right? And the bending stresses are greatest at the surface. So if I run down to the machine shop, if someday it opens again, and I machine this thing, here, I hate looking at the slides for too long. I don't exactly like looking at myself. So let's say this is, I'm bending this thing, bend. And so I run down to the machine shop and I go, I just run this, through the lathe, and I don't do a very good job. I kind of stop to talk to a friend and then kind of keep cranking the thing, whatever. I've got just a bunch of little bumps, right? I'm not going to have an awesome surface finish on this thing. And every one of those little bumps is a potential stress concentration. Tiny, almost immeasurable stress concentration, but it's there for sure. We really need to pay close attention to surface finish, and that's the best way to make things better in fatigue. Mirror polished, 1.0, right? That's just awesome. It doesn't reduce my endurance strength at all. But if I have just some hot rolled steel corroded in salt water, holy cow, 0.1, right? So if I've got an endurance strength of 300 megapascals or whatever, and now I'm going to say it's hot rolled and it's exposed to salt water, it's now only good for 30 megapascals, right? Salt water, corrosion, surface imperfections are horrible for endurance characteristics, all right? So, surface treatments, right? What I can do is take this part and then I put it in a machine. I just basically shoot a bunch of BBs at it, like millions and millions of BBs, and it's called shot peening, right? What that does, that surface hardens everything so that that actually helps. Even though it's kind of a bumpy finish, it got hardened through work hardening, and it winds up being a lot stronger, right? And S3, it's important to note this, like where it fails at 1,000 cycles isn't really affected by surface finish stuff, right? That's more of an intrinsic material property. Reliability factor, I guess that doesn't show up very well. Reliability factor. Now this is saying, well, how reliable do you want it to be? Okay, then I'm going to reduce it. Not really. Remember, this is based on experimental data, right? And so if I were to plot the number of cycles that this thing survived, say I'm only interested in studying, 50, 60, 70, 80, right? I'm only interested in studying 80 KSI, right? And I go out here, and if I plot how many cycles it lasted, it's going to wind up looking something like this. What is that? Oh yeah, the bell curve. I love the bell curve. That could be my next tattoo, maybe a bell curve. But so it's normally distributed, right? So if I just say, if I stick right on the line, right, half the part's gonna be to the left of that, right? Which means half of them will fail before I get to that line. And so if I want to work my way out, to the right end, where so this is, let's make this in blue. So over here, this is very reliable. Very reliable, and then over here that's likely to fail. Now of course, right, we plot this line based on the median, right, the 50th percentile, but if we really want to make sure this thing doesn't break, brake components, rail car axles, whatever, I've got to account for that in my endurance strength. Okay, so summary of Marin factors. Everything you need to know about fatigue on one page? Well, not really. It was supposed to be funny when I typed it, but now it's really not that funny. Basically, a good place to start with endurance strength. So I could say SN prime for most steels is about equal to 0.5. Right, so half the ultimate tensile strength is SN prime. And then I multiply it by all these factors, right? For the load factor, Why is axial 1.0? This should be a 0.85, I think. Let me check on that. I think that's supposed to be 0.85. Why is that there? I gotta check on that. I think if it's an axial loading, it should be 0.85. The bigger the thing is, right, that reduces the endurance strength. Surface factor, right, relies heavily on this plot back here. And temperature factor, we're not going to deal with that too much. It doesn't really matter until you get pretty hot. But for some applications, engine applications, it is really hot, right? So you might need to worry about that on the exhaust end of things. Reliability factor, this is all based on normal distribution. There we go. And so, yeah. So this is kind of the summary of all the Marin factors or fatigue strength modifying factors that reduce the lab-based endurance strength down to what our actual component should be based on. All right, so that's it for that one. I'll talk about the rest of this in a little bit. And yeah, we'll talk to you guys soon.